Good morning, this is Mr. Herman. Since we've been out for a few days, we're going to have to kind of consolidate the calendar a bit. I'm going to use a few videos to go through the notes that we've missed the past couple of days. Okay, so hopefully you've been doing your reading and filling in these double asterisk parts. But I'm going to go ahead and go through each of the next 3 days, day 2, day 3, and day 4 of chapter 10 to make sure we can get that prior to spring break. All right, so the first thing we're going to look at is what are the conditions for calculating a two-sample z interval for p1 minus p2. Okay, the simple thing right here is that we're going to use the same conditions. Okay, so we have random, we have 10%, and we have the LCC. Okay, and for all three of these, we need to do for both samples. Okay. Now, the only thing that's a little bit different that we need to remember from before is that for a random condition, we're also checking to make sure that our two populations are independent. Okay. Now, the standard error for p hat 1 minus p hat 2, okay, this formula is in your book. Okay. So we have standard error, and then we have p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. Okay. Now this is going to be on the formula sheet in a way of speaking, and we'll look at these in class this week. How is this different than the standard deviation of p hat 1 minus p hat 2? Okay. The standard deviation is going to use parameters. Okay. So standard deviation uses parameters. Okay. How is it different than the standard error for a two-sample z-test rather than an interval? Okay, in our test, remember we use this p hat c. Okay, so we are not pooled in an interval. Okay, you're probably asking, well, why is it not pooled here? That's beyond the scope of this course, so we don't need to worry about that. What does the standard error measure? Okay, as always, standard error measures how much the standard deviation varies. Okay, now our formula for a two-sample z interval for p1 and minus p2 is going to be our test statistic plus or minus our critical value, which since we're using a z interval, it's a z star, and then our standard error. Okay, now is this formula on the formula sheet? Kind of. The components of it are. And we'll look at the formula sheet later this week to kind of have a better understanding of what's going on there. Okay, let's go on to the next page. Okay, so we have a question about gun control here. Explain why we should use a confidence interval to estimate the change in opinion rather than just saying that the percentage increased by 13 percentage points. So we've got a 2013 poll that says 38% responded that they were dissatisfied with the nation's gun laws and policies and want them to be stricter. And then the year before, in 2012, only 25% agreed with this statement. Okay, so why do we want to use a confidence interval rather than just saying? It's our key word of the past couple of chapters, sampling variability. It means that the true difference might not be 13 points. It could be more, it could be less. Okay? We've got two, essentially these are going to be intervals, these 38% and 25%. Because we'll have a plus or minus on them, that margin of error. So we're going to kind of combine all those components here and then do a confidence interval. All right, so let's go ahead and do the problem here. So use the results of these polls to construct and interpret a 90% confidence interval for the change in the proportion of U.S. adults who would agree with the statement about gun laws. So we'll start with our state. Okay, so our confidence level is 90%. Okay, Now we need to describe our parameters. Okay, so P1 is the true proportion U.S. adults. Let's see. Let's just say who want gun control. That's 2013. P2 is true proportion of U.S. adults who want gun control 2012. Okay, and we do have one other component of our state that we want to always include when we're doing an interval. We have two samples of we're looking for P1 minus P2. Okay, so our plan. Okay, and I do know we don't have much space here, but our plan, we're going to be doing a 2-sample Z interval for proportions, or rather for difference in proportions. Okay, so our 3 conditions are random. So these populations, they're taken a year apart. So populations are independent of each other, stated random. Let's see, our next condition is our 10% condition. In our 10% condition, we know at least 1,110 U.S. adults in 2012 and 2013, addressing both of our samples. And then our LCC, let's see, we got to do some math here. So we've got 1011 times 0.38, and then 1011 times 0.62. Give me a second. Let's see. It's going to give us 384, which checks out. 627, which checks out. Then we have to check our 2012 sample. 1011 times 0.75. And then we get 253 and then 758. So all of those check out. Cool, so our conditions are satisfied. We are good to go on. Okay, so do. For our do, let's see if this works. Beautiful. Okay, so in the calculator, I'm going to go over to tests. Okay, so you have a 2-sample Z interval for difference in proportions. So I don't want to use sample. I want to make sure I have 2 proportion. And I'm looking for an interval, so a 2 proportion. There we go, Z int. Okay, so let's see. If we look at our problem, for P1 we said 2013. Now in this case, X1 always has to be an integer, never be a decimal, never be a percentage. So I'm just going to take my sample size times my percentage. Okay, and I'm going to go up here and make sure I delete the rest of this. Okay, sample size is 1011. Let's see, X2, we have 1011 times 0.25. Okay, I'm going to go ahead and round this one up out of 1011. Confidence level we said is 0.90, and we'll go ahead and calculate. Okay, so there is our confidence interval. So 0.09592 to 0.16323. Okay, that's all that we need to include in our do portion. Okay, now in our conclude, we are 90% confident that the interval, we'll put it right here, 0.09592 to 0.16323 captures the true difference in proportions between poll results from 2012 to 2013 about gun control. Okay, now this looks pretty similar. We just had a little extra work to do in our state and our plan because we have two samples rather than one sample, but pretty much the same idea here. Basing intervals are convincing evidence that opinions about gun control have changed. When you think about that word changed, that means that if there's no change, 0. Okay, so since 0 is not in our interval, we have convincing evidence to support that opinions have changed. Okay. Now, can we use our calculator for the do step? Yes, we can. Just so we are aware, we can remember we're calling one sample z int is what we were going to want from the calculator. Okay. Interval for difference in proportions. And what that's called, oh my gosh, Mr. Herman, too much. This is called a 2 prop z int. Okay, that's what the calculator will say. Are there any drawbacks? There are. We must use integers for x1 and x2. Okay, if we don't use integers for x1 and x2, we'll be given an error. All right, parameters. This is one of those places where we can easily get our points defining parameters, and we don't want to make mistakes. Okay, so the key mistake we make when we're defining parameters is that we will address the sample instead of the, I call it mistake. Address the sample instead of the population. How can we avoid that? Use present or future tense. Okay, and you'll find out that that's going to help you because if we're looking at a sample and we're describing our sample, we already took the sample, so that's in the past. Whereas we're trying to make a prediction or a claim about the present, the future, if we do this again. Okay, about the entire population. Cool. The reason why it has to be about the population because we're saying the true proportion or true mean, and the true value is the parameter which describes the population. All right, let's go and move on to our next page. Okay, it's called baked beans. For their final statistics project, 2 students performed an experiment to determine if plants grow better if they are exposed to classical music compared to heavy metal music. Okay, so we've got some seeds. We're randomly assigning them. Okay, so that's good. To listen to either metal music or classical music, and the amount of growth is recorded here. State the hypotheses the students are interested in testing and define the parameters. Okay, so if I'm looking at this, we don't really have any proportions here. We're going to be moving on to means. Okay, so rather than p, we're going to be using mu. Okay, so I'm going to use something different here that we haven't really talked about, but hopefully it kind of makes sense. Mu m and mu c. Okay, mu m for metal. Okay, so the true mean growth of metal listening plants. True mean growth of classical listening plants. Okay, now I have to write our hypotheses here. We have 2 mu's, mu1 and mu2. For our Pokemon fans, there you go. And we're trying to figure out if they grow better if they're exposed to classical music. Okay, so we have mu classical equals mu metal. Okay, our null is always equal to. And we're thinking that classical could be better. So let's do mu c is greater than mu m. If you flipped everything, that's perfectly fine. Okay, you're going to get the same conclusion at the end. Some of the steps you get might look a little bit different, maybe some negatives rather than positives, but you should still have the same results and the same conclusion. Okay, what is the evidence for the null hypothesis, or the alternate hypothesis rather? If you calculate mu c, Mr. Herman already did this, he got that it was 85.8, and mu m is 38.2. Okay, so we have evidence. Classical is greater than metal. Okay, and the two explanations. There is actually a difference. And classical music is better. Or what's the other possibility? A good old-fashioned random chance. Okay, random chance, sampling variability. Okay, now we're not going to conduct, but we will design a simulation. One of our favorite simulation techniques is our good old-fashioned note cards. Okay, so we're going to start off by listing all growth heights on 10 index cards. Randomly choose 5 to assign to metal group and 5 to classical. Okay. Then we're going to check the difference in means and graph on a dot plot, and then repeat to generate a distribution. Okay, so we're making a sampling distribution, essentially what we're doing here. Okay, so not really sampling distribution because we're going to do it a lot. It's going to actually make more than a sampling distribution. Okay, so that is it for day 2. If you have any questions, make sure you bring those to class and we will be able to discuss those further.